Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Taufik Ismail. I am 19 years old, a student from Siliwangi University. Here I will explain about mechanical testing of steel.
Many tests are available to evaluate the mechanical properties of steel. This section summarizes some laboratory tests commonly used to determine required properties in product specifications. Test specimens can take several shapes, such as bars, tubes, wire, flat section, and notched bar, depending on the test purpose and the application. Certain methods of fabrication, such as bending, forming, and welding, or operations involving heating, may affect the properties of the material being tested. Therefore, the product's specifications cover the stage of manufacture at which mechanical testing is performed. The properties are shown by testing before the material is fabricated may not necessarily be a representative of the product after it has been completely fabricated. In addition, flaws in the specimen or improper machining or preparation of the test specimen will give erroneous results. ASTM A370. The tension test, ASTM E8, on steel is performed to determine the yield strength, yield point, ultimate tensile strength, elongation, and reduction of area. Typically, the test is performed at temperatures between 10 degrees Celsius and 35 degrees Celsius, 50 degrees Fahrenheit to 95 degrees Fahrenheit. The test specimen can be either full-sized or machined into a shape, as prescribed in the product's specifications for the material being tested. It is desirable to use a small cross-sectional area at the center portion of the specimen to ensure fracture within the gauge length. Several cross-sectional shapes are permitted, such as round and rectangular, as shown in Figure 3.15. Plate, sheet, round rod, wire, and tube specimens may be used. A 12.5 mm 1/2 in diameter round specimen is used in many cases. The gauge length over which the elongation is measured typically is 4 times the diameter for most round rod specimens. Various types of gripping devices may be used to hold the specimen, depending on its shape. In all cases, the axis of the test specimen should be placed at the center of the testing machine head to ensure axial tensile stresses within the gauge length without bending. An extensometer with a dial gauge, Figure 1.27, or an LVDT, Figure 1.31, is used to measure the deformation of the entire gauge length. The test is performed by applying an axial load to the specimen at a specified rate. Figure 3.16 shows a tensile test being performed on a round steel specimen using an LVDT extensometer to measure the deformation. As discussed in Chapter 1, mild steel has a unique stress-strain relationship, Figure 3.17. Here, a linear elastic response is displayed up to the proportion limit. As the stress is increased beyond the proportion limit, the steel will yield, at which time the strain will increase without an increase in stress. Actually, the stress will slightly decrease. As tension increases past the yield point, strain increases following a nonlinear relation up to the point of failure. Note that the decrease in stress after the peak does not mean a decrease in strength. In fact, the actual stress continues to increase until failure. The reason for the apparent decrease is that a neck is formed in the steel specimen, causing an appreciable decrease in the cross-sectional area. The traditional, or engineering, way of calculating the stress and strain uses the original cross-sectional area and gauge length. If the stress and strain are calculated based on the instantaneous cross-sectional area and gauge length, a true stress-strain curve is obtained, which is different than the engineering stress-strain curve, Figure 3.17. As shown in Figure 3.17, for small strain levels the true stress and strain are similar to the engineering stress and strain. The true stress is slightly greater than the engineering stress and the true strain is slightly less than the engineering strain. However, as the strain level increases, especially as the neck is formed, the true stress becomes much larger than the engineering stress because of the reduced cross-sectional area at the neck. The necking also causes the true strain to be larger than the engineering.